Hello, good morning, everyone. My name is Marion. As just introduced, I'm a security researcher with Intel, and I'll be speaking about compiler bugs and bug compilers. In fact, the title is a little misleading. I will not actually focus on compiler bugs that accidentally happen and introduce vulnerabilities into binaries. I will be speaking about how to make your compiler put vulnerabilities into innocent binaries. That means that you could hand me any piece of perfectly well-written source code without any bugs at all, and as soon as I compile it, all of a sudden it is vulnerable to different ways of exploitation. I'll start this presentation off with the very important disclaimer. Since I'm working for a large corporation, our lawyers want me to tell you that the opinions and positions expressed herein are mine only and do not represent the views of any current or previous employer, including Intel Corporation or its affiliates. Yada yada. The last important piece of the slide that I want you to take with you is that no actual database software was harmed in the making of this presentation. This becomes important as I walk through the presentation, and you will see that I used an open source database software to show my compilation magic. All right, now let's get started. Hello, it is me. Again, my name is Marion. I'm a researcher at Intel. I work on compiler internals currently and on all sorts of other CPU-related bugs. And at this point, I have to ask you, please don't ask me any questions about CPU bugs. I really cannot talk to any of this at all. If you have questions about the talk today or feel like you need to reach out, here's my email address and my Twitter account. All right, now let's get started. So when I saw that Hack in the Box has 1-hour talk slots, I was actually very excited and thought I can put everything in there that I've done on compilers. And this is actually what happens. So be prepared, this presentation will be very quick, and you will now walk with me through compiler internals and learn everything you'll need to know in about 10 minutes. Let's start off with me saying that the idea of compiling bugs into innocent source code wasn't mine, but was actually coined more than 20 years ago. So the first time that I found mention of compiling bugs into source code was in Ken Thompson's 1983 Turing Award lecture, where he pointed out that compilers are neglected in terms of security consideration. He showed that he can compile a bug into an innocent piece of source code. And it turns out since 1983 until today, not much has changed about that. You can still, if you get your hands on a compiler and are able to compromise the compiler itself, you're still very much able to compile bugs into binaries. And those might be very, very well visible if you have a good security team. But even if you have a good security team, you can also very well hide your bugs into binaries, even there, so that they're very hard to find. And this is something else that I want you to take with you throughout this presentation. Back then, when Thompson gave his lecture, it looked very simple, and it seems very straightforward to compromise a compiler and make the compiler do whatever you want in order to insecure the output binary. In fact, though, whatever you do in a compiler, especially in a modern-day compiler, is really hard to be of any use for the community. In some sense, if you see publications about compiler modifications that propose mitigation ideas, that propose mitigating entire bug classes, or that propose, as I do, compiling bugs into binaries, keep in mind that it is not always as simple as it looks like. And if a POC looks very straightforward, then possibly it is not applicable to most source code bases. Compilers nowadays are very complex creatures. They produce binaries that are very complex in their format. Those binaries are loaded by loaders that are very complex in their structure. And in the end, those binaries will be executed by operating systems that are very complex. So all these complexities together make our compilers nowadays really, really sophisticated. So whichever change you plan to apply to a compiler needs to be very well thought out and very well tested. Today, what I'll be focusing on is the GCC compiler. GCC is an open source compiler. Most of you will have heard about it, and most of you will have used it at one or another point. Don't ask me why I'm focusing on GCC. Turns out that since I work for Intel, we love to work on projects that we use internally, and turns out that LLVM nowadays is mostly used by hipsters. I did not say this. Most of our firmware turns out today compiles with GCC, which is why I was told to focus my research on GCC. And again, the project that I'm talking about today is not directly linked to what I do at work. At work, I focus on researching compiler mitigations. Just turns out compiler mitigations aren't nearly as interesting as compiler bugs, which is why I'm here today. Most of the presentations and blog posts and documentation and whatnot you will find about GCC starts out with this picture. This is the publicly understood 10,000-foot distance view of GCC. It looks nicely well structured. It has three main components, which is the front end, the middle end, and the back end, and there's the different compiler steps neatly listed in this graph. In reality, GCC is a monster of 14 million lines of code, and the source base isn't nearly as well structured as this picture. But let's start out with this picture. So, of course, at the beginning, you have the front end, where you look at different versions of source code, like C or C++ or Java. Or in reality, if you're a developer and you extend the GCC front end, you could write your own programming language and have GCC compile it for you to any given architecture that GCC can compile for, because those parts are neatly separated. You have the front-end parser, which generates the abstract syntax tree and lowers this representation to the generic representation. Generic, in theory, is a source code independent representation. It looks about as weird as you would expect if you try to put C and Java in the same intermediate representation, but this is what we have today. And from there, the compilation process goes on and lowers the generic representation into different other representations, which help the compiler find ways for optimization and help the compiler lower the last stage down to what we today know as machine code. Those stages that are important for us today are GIMPL and RTL. GIMPL, as you can see, is more close to the actual source code that was put in, and RTL is more close to the actual machine code. Every time I mention that I work on compiler internals, people start out with, oh yeah, this is really complicated, all those optimizations. And I'll tell you, I've been working on GCC for more than a year now, and I have not ever touched the actual optimization settings or the actual optimization passes of GCC. I'm just not there yet. I've mostly been focusing on RTL and GIMPL as the different representations, where we could tap into either secure source code or bugify source code, or secure the to-be assembly representation or bugify the to-be assembly representation. And this is what we're going to be speaking about today. GCC isn't only theoretically comparted into different modules, it's also theoretically parted into different passes. So you can imagine you have the 10,000-foot view. If you look at the compiler passes, you're like at the 9,000-foot view. The GCC passes are organized to perform different dedicated tasks on the source, or like on the different representation as they wind through the compiler. In the beginning, you have the C source code, and at the end, you, for example, have the x86 binary output. The passes by itself, there's plenty of them. Depending on which optimization setting you use, you have either between 100 or 300 passes that the compiler performs on the binary, or on the, how do we call it, source code to be binary. Important for us, if we want to perform changes on the state of what our code is in, then ideally we create our own pass and perform those changes in a given pass. Important to note at this point is that GCC, like the passes aren't nearly as well separated as we would expect. In fact, there's different data structures and different representations that GCC uses internally that are available throughout the compilation process at different stages. So for example, if you would go ahead and wanted to change something about a given register that is used in the outputs, let's say you're focusing on RBX as an x86 register, then you would need to locate where in your compilation step this register is present for you to get your hold on and grab on. So for example, if you're at the beginning of the RTL passes, your representation is still very generic. It is independent of any given machine architecture. And only throughout the different RTL passes, the generic representation of RTL will be lowered down to a more machine-specific representation of RTL. And somewhere in those passes, you'll find the register allocator. After the register allocator, typically you have access to the different registers. And this process is true for anything you want to change in the different representations of GCC. So the passes are somewhat important for us. What is more important for us than knowing the different passes is the debug output. Turns out there is a very thick book that tells you about GCC internals and about the different data structures and their availabilities and whatnot, and it's about 800 pages thick, I think, maybe even a bit more, and it doesn't teach you at all how to perform any changes in GCC. It is a very good book, it is very neat documentation, but if you want to learn how the different passes look like, how they interact, how the data structures look like, how their representations look like, you could best go about it in looking at the debug output. There's different compiler switches which help you print out all the different representations that GCC has available. Most importantly, there will be fdump3-all, IPA-all, and RTL-all. This gives you the biggest collection of pass dumps that GCC can produce. And if you go ahead and insert your own compiler pass, you can dump the representation that your compiler pass produces with fdump RTL my awesome pass. This gives you insights in the changes that you perform yourself, which is very helpful. Now, I've been talking about compiler modifications. If you ever try to modify your GCC compiler and recompile with the changes and start testing your changes, you will notice that you spend a lot of time compiling, which makes it very unfeasible to work on the compiler source code itself. Thankfully, since GCC version 4.5, we can introduce plugins which have almost the same power, the same availability of APIs and data structures as you would have if you would tap into the compiler source code itself, except that plugins are easy to compile and easier to load than your personal compiler changes. Most of the POCs that I'll be presenting today were implemented using GCC plugins, but keep in mind, anything you do in a plugin, you can naturally also do in the GCC source base. Plugins are neat for developing and extending. If you rather apply your changes to a compiler itself, you can take the plugin source code and easily integrate it with GCC. I say easily to quick. It might not be easy, but it's possible. The GCC plugins themselves are a little bit more limited, so you might not be able to port any given change to GCC to a plugin, because by nature, the plugins don't have access to all of the data structures that GCC provides. However, we can write plugins that tap in as early as the generic phase, which means after the abstract syntax tree is lowered to generic, and as late as the last RTL pass, which is almost x86, but still, or almost the machine language, but still compiler representation. And this is about enough to be able to insert bugs into code. We're almost done with GCC, and now you're all experts. As a final note on GCC, let me tell you that I've been talking about, like, you can dump intermediate representations and look at them and understand which changes you did to GCC, and it sounds that simple. It is almost that simple, but it's not exactly as straightforward. A couple of years ago, when I was learning x86, I got used to look up different instructions and see how their behavior works and what their conditions are and what their output is to be expected. And I went in with the same expectation, looking at the Chimple representation or the RTL representation of GCC, and turns out RTL especially is a little bit more complicated. RTL is what you would expect to be a generic assembly language that can be translated into any given architecture. So in there you have not necessarily, in the early stages, you don't have the registers you would be used to in your architecture. You don't have the memory restrictions you would be used to in your architecture. In fact, in the beginning, RTL has an infinite number of registers available, and only when GCC learns which architecture it will compile to, it will apply the architecture-specific limitations to the RTL representation. This screenshot I took in one of the later stages of RTL, where we already have registers assigned. And this piece, as complicated as it looks like, translates to two instructions, which would be LEA, like load a string into the RDI register, and then call the put function, put string. So we load an argument into RDI and then print that string. And as you can imagine, a given output binary has millions of instructions if the source code is big enough. A given instruction in RTL occupies at least 2 and like a maximum of 5 to 10 lines of code. So if you dump all of the intermediate passes of your large application, you will end up with a lot of log files, and they're very big. Just to keep this in mind. But yes, in order to modify the intermediate representations of GCC, we better get some understanding of the intermediate representations themselves. I'll leave it up to you if you're interested in compiler research. There is a couple of publications out there that are really helpful in getting up to speed, that show example source code. And also there was Emisi Refvi, a researcher from Hungary, and her colleagues, I'm not sure whether it was colleagues. So she was working with the PAX team on a couple of GCC plugins that were earlier committed to the Linux kernel. They're very elaborate and they show a lot of best practices when trying to write GCC plugins. All right, this was the introduction. Let's get to the first demo. Look at this line of source code very well. This is what I'm going to show you now inside of GCC. And I hope I got my demos all very well set up. And here we go. No, we don't. Where? Duplicate? Please? Yes. Whew. So I'm a hardware researcher, but I have no idea how beamers work or why they ever do what we want them to do. Here I'm in a folder where, maybe if you can read what's on the screen, there's a hello world.c, which I'll show you will print nothing but hello world. So you can see here there's a printf hello world and really nothing more. Okay, but there's also a malicious compiler plugin in this folder. So now if I go ahead and just compile my hello world without any plugin interference, I can execute my hello world, and surprisingly I see it prints hello world. If you can see that too, just believe me, it says hello world. Now if I go ahead and load my super malicious compiler plugin, I can still compile the hello world.c, and now if I execute hello world, all of a sudden it says hail Satan. How did that happen? I'll tell you, if you're inside of the compiler, you have superpowers. Whoops. There we go. So this was hello world. And this is hail Satan. What I did in this tiny little plugin was essentially, I just looked for the chimple call to the put string function, which would output the hello world string. And I located the argument, which you can see here, where's my pointer? Chimple underscore call underscore arg will give us the first argument of our put string function. And in the end, I did something super simple. I created a new argument, which was the string hail Satan, and then called the function chimple call set argument. With this function, I essentially replace the argument that's in the call to put string and can put my own string in there. Now, with this little example, you will see in the compiler you have superpowers and can do lots of very obvious stuff. You can go ahead and change string arguments, which is rather pointless. But you could also go ahead and change buffer sizes. You could remove sanity checks. You could remove whole pieces of source code. You can replace whole pieces of source code and add entire chunks of logic. You can tinker with authentication checks. You can make crypto functions a lot more insecure than they should be. You can be very obvious about what you do, and you can be very sneaky about what you do. As a defender, you're in a hard position there because reviewing binaries is very, very hard. If you're like a company that puts out a significant amount of software, then it is difficult to find as many reverse engineers that would help you look for bugs that the compiler put into the binary. What you can do, though, is you can diff and see whether anything was added or removed from what you would expect to be in a binary. You can try to fuzz, of course, which we should always do on your own binaries to see whether there's any bugs in there you wouldn't expect. You can try to guard your build environments, which is rather kind of obvious. Don't let anyone go ahead and tinker with your compilers like I would. And of course, I don't know how many people in the room ever thought about doing security review on their make files. I'm not sure whether that's a common habit to do. I would recommend to do so every once in a while to see whether someone might have sneaked in a plugin that's being loaded in the compilation process. All right, another thing that would be rather obvious is to attack a piece of source code that already had bugs in it in the past that were patched. If you look at what was patched in source code in the past, you can easily go ahead and spot a patch and through the compiler remove that given patch, which is how I started my whole adventure into introducing bugs into binary. So I picked up a bug that was reported last year by a member of Project Zero from Google, where they found out that a file name was checked for a given dash. And the routine that was looking for the dash in the file name was expecting the dash to be naturally there because it's an SQLite, or it's a database internal file that's being passed. So that routine wouldn't look for the end of the string. So we just keep on looking for the dash forever, and afterwards, very conveniently call a memcopy function to copy the parsed string name into a given buffer. Doesn't look bad at all, right? So I went ahead and picked up that open source project, which is SQLite, which is why in the beginning I mentioned there isn't actually more bugs in SQLite now that I did my project as there were before whatsoever, but all the bugs that I show in this presentation were my work that was just me, and SQLite might be perfectly fine still, hopefully. All right, so I went ahead and unpatched that bug. Let's see how that looked like. Since I work for Intel now, I start most of my slides on the right side and work my way to the left side. So we have to begin over there, where we see the original source code as it is compiled with the patch. You can see I marked down there a compare instruction, which looks for a 0. It compares a given character. This variable over there is a character. It sees whether that's a 0, which would indicate the end of a string. If it reaches the end of a string, then this loop that we're in, where we're looking for the dash, is jumping to an error handler function, says we didn't find the dash. Originally, this check wasn't there, and after I compiled SQLite, this check wasn't there anymore either. So over there on the right side, or on the left side, you can see that these two instructions are now missing. That was my proper work, and it turns out I had a closer look at this bug. It is actually not very helpful. The routine looks for this dash, and if it can't find the dash, it will continue execution until it finds a dash, which could be anywhere. And for me, as an attacker, there was no way of actually putting a dash somewhere in memory where I could control the location of the dash and control the content of the buffer until this dash is found, which means that there is no other way than to segfold with that bug. And later on, I started wondering, is that true? So with the source code as it looked like at that point in time, I couldn't do much with that bug, except if I could run another plugin and look for what I could do to make this bug actually more accessible and more controllable and more exploitable. So I went ahead and did the obvious. This function actually takes in the database name, or the path plus name string that indicates where the database is located, or where the file is located that SQLite should be opening. And said and done, I went ahead and looked where this path is being read, which function it is, and how it wanders down through the SQLite function stack until the moment where the memcopy operation is happening. So follow me in my adventure in GDB, where I found out which function it was where the memcopy was happening, which is called find create file mode, which does create a file at the end and contains the vulnerable memcopy function. And throughout the stack, I figured out that the function SQLite3 pager open was the one which performed certain checks on my file name, which prevented me originally from introducing my properly crafted file name in order to exploit my memcopy bug. So I went to that function and checked, looked for the security checks that are performed in this function, and figured out we have a call to a function called SQLite3 OS full path name that you can see in the upper half here, which takes in the provided string, performs security checks, or performs sanity checks in that string, and copies it to a different buffer, which in the continuing source code will be used as the actual path name to the SQLite database. So what I did as an attacker was I located that function, I figured out this is my problem, and I removed it. More about this in a minute. The other check that I was curious about was down here, where the length of the path name was compared to a given max path name variable. This is also very destructive if you try to enter a path name that's just too long. So I went ahead and wrote a plugin, which simply goes ahead and locates those checks and removes them. The first one was removed by just assigning the pointer of the path name that was to be checked to the pointer that would contain the checked path name. In the end, skipping the validity checks that were performed by the function mentioned before. And the second thing I did was I located the condition that checked for the max length variable and just flipped the output value. So when you look through the Chimple API, you would almost think it's written for an net ticker, because you can replace arguments, you can replace values, you can increase values and lower values, you can switch arguments, and you can negate or positivate, however you say, like flip the outcome of logical conditions. And it is also rather straightforward to understand. Like Chimple by itself is not the most complicated language. All right, let's see how that looks like. Oh, and one more slide. This shows my massive exploitation skills. I have to say at this point, I'm not a Linux specialist. As much as I'm talking about Linux, I'm born and raised on Windows. And neither am I a GDB specialist in any sorts, and neither am I an exploitation specialist. Anyhow, here's my mad exploitation skills, where we're at the end of the find create file mode function, where essentially I overflowed my memcopy operation. That memcopy gladly copies stuff to the stack, and gladly GCC decided that in this particular function, it doesn't need to apply any stack cookies, because there's no input coming from an outside function, because the checks were performed way earlier, and clearly GCC didn't see me coming. Anyhow, so I entered a very long string as a database name. Seems very simple and straightforward, and in the end managed to overwrite the return value on the stack. And this return value, I wrote the address of my own little shellcode that since I'm the compiler, I also compiled that into my binary. Anyhow, this is just a demo. If you're more versed in exploitation than me, then feel free to exploit this bug yourself. Good, demo number 2. Whoops, wrong one. World, Nginx, escalate. What? Ow. First I have to find my demo. Here we go. That happens if you have too many windows open. So in this directory, I prepared the perfectly innocent source code of SQLite 3 and my own plugin, which... Oh, sorry. The plugin is in a different directory in this case. And in this directory, we have the source code of SQLite 3, and we have a little database application, which I will show you right now. The database application, as you can see, is not actually fit for execution at all, because, as mentioned, I bluntly just put a very absolutely useless database name in there. This is my neat little stack buffer overflow. Don't look at it too closely. It is not crafted very well. Anyway, exploitation is not what I wanted to show you today, but compilation. So now, as I go ahead, I pre-built, where are we? I pre-built the lib SQLite 3.0. This is the SQLite library. One of the reasons why I picked SQLite as my victim, because SQLite has a very neat amalgamation release, which means that all of their source code is located in one C file, which makes compiler tests very easy. It's just like one large source file, and you don't have to care about build chains and whatsoever. You just execute GCC, and it will compile the whole database library, which is very neat. Anyhow, what was I going to show you? I have this script which compiles my useless database application. It's called compile and run, which, if you have a look here, in the middle of the script, the first couple lines are set up. In the middle of the script, you see that I call GCC7 to compile my database application, which is called dbtest.c, which is what I just showed you, has this extremely long file name, which won't do anything at all. And in the end, we execute that application. So let's go ahead and compile it. And of course, SQLite will tell us that it cannot open possibly this file name, which is good. We're still secure. There's no bug in there whatsoever. But now if I go ahead and start recompiling SQLite with my prepped makefile, where we tell GCC to please unpatch the bug that was in there. I'm now executing make with an unpatch equals 1, which means that if you look at the line that is shown right here now, we're loading the chimpleattacker.so plugin, which in the end will remove all the sanity checks and unpatch our overflow bug, and in the end make the application vulnerable. Woohoo, there we go. Now we have an SQLite database library, which is absolutely vulnerable to our attack. And running my test again, and woohoo! All of a sudden we have it's not a calculator, sorry, I couldn't find the calculator, it's an abacus. Turns out Debian doesn't ship with the calc.exe. Anyhow, there you see, like I just overflowed the buffer, I captured the return address, I loaded it into EIP, and I redirected it to my little piece of shellcode that I compiled into my library. And all of a sudden, we see an abacus here. Good. So you see, we can perfectly well unpatch bugs, we can introduce bugs, we can modify so much stuff in the binary. And something that I'll have to tell you about this is that is not quite evasive what I did there. So I made major changes to the actual source code. If you flip stuff in the source code and remove and add things, you're always performing changes that at the end of the day might affect your future execution. So the checks that I removed might have been vital for some other operation that used the same function as SQLite. Especially if you use large applications, it is very likely that if you go ahead and change something in the source code, it will be a problem for you later on, and you have to fix all the corner cases where your changes actually create problems. A thing that I've been thinking, going through the source base of SQLite, was that they use the same sanity checks all over through their code. So if you would just go ahead and look for all the mem copies, they use a lot of mem copy and use the same sanity checks. And if you generically just change those sanity checks, you cannot be sure that the application still properly executes. This is a thing to keep in mind. That said, there's lots of do's and don'ts when you go ahead and load such changes into a compiler. First of all, craft wisely. Once you get going on simple plugins and you can do changes in Chimple, it is pretty straightforward to change arguments and change numerical values and replace function calls and whatnot. But in the end, as I just mentioned, you have to keep in mind that your changes might affect other parts of the binary as well. And as mentioned in the beginning, compilers are very complicated, and whichever change you do inside of the compiler might affect other important pieces of the compiler that you have to keep in mind. This becomes more and more true, especially as you move down lower the passes. So in the beginning, the closer you are to C, the more natural it is for you to change a function call to another. The closer you move to the actual x86, the more you have to keep in mind, how does your output binary format look like? How does your loader load the binary? Like if you perform changes to the header or to the actual representation of the code, how does the loader deal with that? Afterwards, you have to consider that your operating system wants to execute the binary on your machine, on your actual CPU. And you have to consider, for example, if you perform changes to how registers are used or to change how the stack is being used, then you have to know what else is affected by your change to the stack. If you just add a given push instruction in any given function in the middle of SQLite's execution, you will crash because you will mess up the stack frames. And this is bugs that, in the end, if you write a large plugin and do lots of modifications and don't perform proper testing, you will have a very hard time finding those bugs. I'm speaking of experience because, as mentioned, I tried to implement mitigation prototypes in GCC, and I found lots of those bugs that were very non-obvious to me in my debugger. So that's it. Test properly whichever changes you perform. Refrain from making any assumptions. There's lots of APIs inside of GCC that their names sound very obvious, but if you don't understand what's going on in them, please don't just use them, but understand what you're doing there first, because otherwise you might insert bugs that are very hard to find into your own bugged binaries. And debugging binaries that the malicious compiler spit out isn't always that much fun. Consider the target as mentioned, consider how stacks look like, how registers are being used. For example, do not perform any changes on RBX in a binary that's compiled as a position-independent code, because RBX is typically used to locate the linker table. If your binary dynamically wants to look up where the linker table tells it to find a given API call, then changing RBX is not recommended. And as you see, this explanation was very long. I had a very hard time figuring out what was wrong with my usage of RBX when I ran into that bug. Again, compilers are complicated. Also, something to keep in mind is that compilers change, or GCC changes occasionally a lot among the different versions, and something that you've been doing in GCC version 5 might not be applicable anymore in GCC version 6. The same applies to version 7 and 8, and this will sadly be true in the future as well. So if you're not exactly sure which compiler version your victim will be using, then essentially the amount of development effort that goes into a plugin or a change rises exponentially, because you have to consider the different versions of your compiler. All right, we're almost halfway through the presentation, which is good. Let's get to the ELF things. I actually only added this slide because I thought the ELF was so funny. What I wanted to talk about with ELF things was that the ELF format itself offers us many ways to perform simple modifications that help us execute malicious code in there. This just as a side note. There is a nice documentation of the ELF format, which I totally recommend. If I look up cs.stevens.edu, they have this nice long explanation of what the different ELF sections are there for. When I look through the documentation, I noticed there's something that's called the init array section. This is an actual binary section. And as you can see in the documentation of that init array is that it contains pointers to functions which will be executed when the program starts. And I was like, oh, this is exciting. So that means if I put just any given pointer in there, then the binary will just execute wherever that pointer points to. And it turns out this is exactly what happens. And the ELF format, I'm perfectly well aware this has to be that way. But the ELF format offers different sections like that, which offer exactly the same mode of adding functionality to a binary. This is typically what the compiler does. Just imagine you're writing C++ source code, and the compiler for you adds a constructor to the binary, which needs to be executed on load time. Then it would add that constructor to one of those pointer chains, which means that this constructor will be executed. And this is all perfectly well and benign, except when you're inside the compiler and want to abuse it. So I went ahead and wrote a simple proof of concept, which is really very straightforward, where I added a given function, which will execute another abacus to my victim binary. And as simple as it sounds like, it is one single function call inside of the plugin, which will add this as a constructor to my init array section. On the source code here on the left side, which you can see, is a simple function which is called output pop funclet, which does nothing else than popping another abacus, which literally just adds a given function to the output of GCC. At this point in time, let me show you the demo, and then we're going to talk about how this is working. Demo, victim, intrinsics. Oops. Init array, here we go. So this is what I've been talking about. In here, the init array demo folder, we have a file that's called test.c, which is very useless as well. All it does is it contains a super pointless function, which initializes an array with -1s or with FFs. And it is called in the main function, and the main function also prints that there's absolutely nothing to see there. So you can see that this source code will not do very much if we execute it. And as we would expect when we compile it without any interference, we can see that the test binary really just prints nothing to see here. This is all the binary does. Very exciting. But if we go ahead and compile it with my little init array modification, you can see I load the plugin, which is called pops.so. We compile again, and all of a sudden we execute the test binary, and there's another abacus. Surprise, surprise. How did we do this? Back to my presentation. There we go. How did we do this? So again, by calling this function called default elf init array as an out constructor. Very self-speaking API names inside of GCC. If we call that, we can add a symbol to the init array section, which in our case points to a function which is called pop_funclet. By creating a symbol reference in GCC's RTL stages, we create an actual pointer to a given symbol, which will be added to the symbol table of the compiler. And instruct the compiler to output that to the assembly output. On the left side of the screen, you can see, as mentioned, the construction of that function. So first of all, we need a symbol that points to our function, and of course, we need to output the function itself. It only took me about a month to figure out how to add a function inside of the compiler, which will end up in the actual binary. And if you look at this closely, you will see that there's lots of printfs in there and actual ASCII strings that show assembly instructions, which for me in the beginning was rather confusing. Because yes, really, we use printf to print to the asymout file inside of the RTL plugins. At this point, I have to say I'm not exactly sure this is the best and most beautiful way. It was the first and only way that I could find how to actually influence the functions inside of the output binary. And I'm talking here like it's an output binary that I'm modifying. fprintf is important to mention because what GCC itself actually is not one binary, one compiler that does the whole modification from source code to executable. GCC by itself is just a driver which instruments different tools that GNU provides for compiling binaries. GCC itself stands for GNU Compiler Collection. You might have heard that before. And that actually means that GCC itself is the compiler. If you're compiling C files, that would be CC1. It is also the assembler, which is the GNU assembler, also called GAS or AS, which takes in the assembly output, the text-based assembly output from the compiler, and assembles it into bytecode. And at the last stage, you have the linker, which takes the output bytecode and links it together to an object file or to an executable that one can load. Here to be said is that what the compiler actually outputs, or what you can do when you work on plugins or inside of the main GCC source base, you can modify how GCC outputs the text-based assembly representation, which is why fprintf is great if you actually want to add functions to the output source code. If you ever want to try, you can execute GCC with the des flag, which gives you the assembly output instead of the binary that GCC would create. That means that the compilation process stops after CC1, and you only get to see the text-based assembly representation, which can then be consumed by the AS tool, the assembler, and further modified to the actual bytecode. This is very helpful for us, though, which means that if we apply modifications to the GCC base itself, we can check in the assembly output whether our assembly actually ended up there. And what you see there is the pop funclet that I introduced to the source. And in there you see the call execl, which I just wrote in there as a piece of text. And now here's a nice piece of homework if you want to try. Write a simple C file, which doesn't import any headers, but just executes a call to an execl and executes an application. And you will see that your compiler still compiles it, your linker still links it, and your system still executes it and executes the call execl. Because as it turns out, the glibc, by default, if you don't set certain compiler flags, is used to compile and link any given C file that you compile on a Linux system. Which means if you're an attacker and you're modifying the source code and you're adding calls to functions that are located in your glibc, if the binary is not compiled without the use of GCC, which is a dedicated flag that needs to be mentioned, then any call you insert there will be happily picked up by the linker and happily added to the linkage table and happily executed at runtime. You do not actually need a given header file to be included or a given library to be explicitly included. This was about it. This is how it looks like. We have the assembly finally. This is the object about. We have the assembly in the file. And you can see in the init array section, you have a pointer, which you see down here, to the actual pop funclet function. Wee-hoo. Super simple and super obvious if you're looking for source changes. So I got this needle. Someone please give me a haystack. I mentioned before, it's kind of obvious if you add a plugin binary. Plugins are shared libraries that need to be somewhere in the file system, and the GCC command line needs to know where those objects lie and needs to know that it has to load those into the compilation process. So it is kind of obvious if you want to place a plugin into the build chain. The problem that arises there, though, at some point I tried to actually look into a compiled plugin, try to figure out what it does, and turns out if you don't know how GCC works, and if you don't know how the intermediate representations look like, all your reverse engineering skills will just tell you how the assembly inside of the plugin looks like. It will not tell you at all what this plugin does. So thinking about forensics investigation that tries to figure out which changes a given plugin applied to a given output binary are absolutely mute. I'm saying absolutely. If there are some motivated reverse engineers in the crowd that can happily share a plugin and you try your luck, it would be interesting to know what you find in there. On the other hand, if you want to be more stealthy and not load a plugin, you can still modify GCC itself. As mentioned, you have the same superpowers in there as you have in a plugin. It might take a while, though, until your changes are actually applied to the compiler. And stealthily recompiling GCC on the victim's machine isn't all that easy. All right, as mentioned, binary code review is kind of pointless, and reproducible builds will be what helps us find the actual bugs that the compiler can introduce in there. But let me go ahead and show you some more stealthy ways of adding bugs to binaries than just putting additional source code in the output. So let's go to the less obvious stuff. Something that I found out while modifying indirect calls in a given source space, because it turns out nowadays everyone's really interested in indirect branches in files. I did not say this. Turns out that this undertaking, you eventually will run into tail call optimization. Tail call optimization is something that not only GCC, but also other mainstream compilers perform, where they try to reduce the number of calls that are done in a binary and try to eliminate them and replace them with jumps, given that at a given point in time when a call is executed, the stack frame from the calling function is equal to the stack frame that the called function will use, which means that a function that is called within a different sibling function, which reuses the same stack of arguments and can reuse the stack frame of the calling function, will be converted to a jump because there need no changes be taken to the stack frame. It is all a little bit... Here we're talking about compiler optimizations, and try to get your mind in there in detail. What's important for us is that this is indicated by a J flag. So in the intermediate representation, you see a call instruction swimming along, and all that diversifies this call instruction from a regular call instruction is the J flag, which tells the compiler to, instead of call, put out a jump. Now, what do we think as attackers if we hear call instead of jump and jump instead of call? This is like, if we modify a jump into a call that would work just like the jump could, then we can sneak in an extra return value to the stack and make our application return to any given other spot where we want it to return to. Easier said than done. Let's look at this output for a minute, which comes from the compiler explorer, where we see this simple piece of source code which shows that there is a printf call, which is located right before a different printf call, can be modified into can be optimized as a tail call. If we don't apply any optimization, this is the output of the compiler without optimization. You see in the yellow part down here, there's a call to put string. This is unoptimized. This is one call after another, as you would expect the compiler to put out. Now, if we apply tail call optimization, all of a sudden, our output looks like this. We see that the yellow line has been split up down here into one move instruction and one jump instruction, which essentially is the same as this call to printf up here, except that down here we use a jump and reuse the call frame of the function up here. Because you can see that the layout of the arguments is pretty much the same. This is what tail call optimization does for you. All of a sudden, at the end of a given binary, and this, again, this works only at the end of a given function, all of a sudden you see a jump instruction there, which should be a call instruction. It only works at the end of a function because the jump that we're using will jump to another function, which will eventually execute a return statement. And this return statement will fetch the original return value from the stack that the calling function was using, which means as soon as the called puts down there returns, it will return to the caller of the caller. And this way, with chaining these returns, we can save one return and we can save an entire construction. What's it with the constructions? Constructions use up a lot of time and CPU power, and they're very expensive in terms of execution. So if you can switch a construction to a jump instruction, you can save those valuable milliseconds that optimization is after. If you want to optimize this, it's fairly easy. We have to locate a function where our changes are feasible. We have to locate a function where if we change a jump into a call, we do not mess up the stack. The stack is important and the stack is vicious, and any change to the stack will eventually come back to you and hunt you. And of course, we have to watch out. In most cases, if you're in a real application, you need to take care of the changes you do and revert them after you modified your return value at one or another end. And you will need to do cleanup and save values and restore values. This is something that just comes with the nature of the thing. And again, here, the register allocator isn't your friend either. You have to watch out which registers you use and whether those registers are still available once you return from your malicious function. And of course, the linker isn't our friend too. Something I found out when working on tail calls is that I have very little control over where in the source code a given function will be located that I put in there. Running out of time. Let's go a little faster. Again, no database software was harmed in the making of this presentation. I didn't actually mess with the SQLite source code, but happy enough, I found a tail call inside of SQLite, actually in the SQLite 3 open function, where you see that open receives those two arguments and then calls open database, which has a very similar stack frame and receives the same arguments extended by a couple more. Now, if you look at this in a disassembler, we see that originally, without optimization, or without our modifications, the malicious modification that we put in there, the call will be tail call optimized, which means the call to the open database function will be reduced to a jump, which means that when open database returns, it will reuse the return value that SQLite open would have been using upon its return, and jumps 2 stack frames upwards, which means when open database returns, it will return to the caller of SQLite open. Beautiful. Now if we go ahead and modify the binary, we can switch this jump instruction into a call instruction, which means that we end up having an extra return value in the stack. And all that we essentially need to change to modify the behavior of this return, of this chain return effect, is that we have to sneak in another address which will be returned to. This is like overriding the return value of a function, just that the compiler does it for you. That also means, though, our malicious code needs to be located in the binary already. There's very little possibility of sneaking shellcode in there. And the bigger problem that we face there is that we have to trust that the linker puts a given function which contains our malicious activity right after the tail call optimized function. In our case here, I went ahead and modified the function that's located right after. In reality, that's a little bit more tricky, and added another call to execl, which in the end will execute another abacus. For the sake of time, I see I'm running out quickly, and I have one last demo, which is more interesting. I'll skip this demo at this point. But be aware that the things that you need to keep in mind if you perform these kind of attacks is you need to be aware of the stack frame. You need to spend lots of time on analysis how the stack frame is used after your jump/call, and make sure that you do not mess up the layout. What happened when I wrote this proof of concept was that 3 functions further down after the call to open database, there was a function which fetched arguments from the stack, which in 64-bit is rather unlikely, but it happened. And at this point in time, the stack layout would not be the same if I wouldn't fix up the stack layout before I actually execute the jump. This is rather easy. I just sneaked in one pop instruction, and the attack still worked. That much to be said. But okay, we're almost done. Let's switch to the last, and in my opinion, most interesting way of attacking. In a conversation with a peer of mine, we figured that all of these changes are rather obvious, because you're changing a lot about how the output binary looks like, in terms of added changes as well as in terms of added behavior. Because as you can figure out, if we have to fix up the stack layout just so that our attack works, we're still adding a lot of changes into the binary. Much easier it would be if we used GCC internal functionality to perform the actual attack for us. And another thing that I wanted to achieve was to produce configurable bugs. You will see if you modify your compiler to introduce bugs for you, you're very much set in these changes that you perform to the compiler, and afterwards you have to trust that the compiler essentially perfectly well performs its thing. Easier it would be if we could modify our own compiler bugs. This is when I came across built-ins and intrinsics. Built-ins and intrinsics are a very interesting subject. It's also a very large piece of code inside of GCC and rather complicated. The simple explanation would be that built-ins and intrinsics are there to add functionality to GCC in order for GCC to be able to produce better output, which would mean that, for example, machine-specific functionality is formulated in intrinsics, or functions that are frequently used and easily optimized by GCC are formulated as built-ins, so that GCC can pick which implementation, for example, of the putString function, or which implementation of a given memcopy it wanted to use. This could look as follows. If we look at this very simple source code example over here, we see a memcopy, which copies a useless buffer into another useless buffer. We see if we compile the source code without optimization, again, we get one call after another and everything's very clear and understandable. As opposed to when we optimize as much as we can, we see that the whole piece was reduced to 3 different instructions. This is built-ins for you. This is where GCC found out that the string-line function is absolutely useless because we're looking at a static string. At the time of compilation, we know how long the string will be, and the string is constant, it's not modifiable, so we can just skip the string length and replace that value with a 6, because we know it's 6 characters. And also the memcopy function down there, the entire call is rather useless because we can replace the copying of 6 bytes with 2 move instructions, where we split up in 3 and 3 bytes and copy those to the actual destination. So this will be what built-ins are. And in that case, GCC needed to know how memcopy looks like inside, how the input values look like, how their nature is like, how the rest of the binary is laid out in order to perform this proper modification. And if you're interested, you can go ahead and monitor optimizations in GCC a bit more. It's fairly interesting to see which changes GCC applies to memcopy. A neat little exercise would be, for example, to walk with grep through all of the output dumps that GCC provides, and see where in the output dumps the different calls to memcopy pop up. So if you have a binary which just executes one memcopy, you can see, for example, without optimization, you can see that call appear until the last stage of compilation, and with optimization, you see it disappear right after the chimple passes. Which means in the RTI representations, you wouldn't be able to access this call instruction anymore. What we could do as attackers now, what we could be interested in, is extend a given memcopy and make it more efficient by copying more bytes. So one of the projects I was working on was trying to spot built-ins as they are being inlined into a given binary. What you can do in a compiler plugin is you can tap into different passes, and you could essentially go ahead and watch in which pass a given call disappears. So what I did was I wrote a plugin which looked at a very early compilation stage and located my memcopies and where they were, stored the location of those memcopies, and then tapped into a very late compilation stage where those memcopies are already inlined and there's no more call to memcopy visible, and located those inlined instructions and just extended them with a 1-byte copy. 2 more minutes. How many minutes can I use up? I really wanted to show you this proof of concept. Let's skip the theory. Let's look at how it actually looks like. So the last thing for today. 5 more minutes. Good. Good. 30 seconds POC. What I wanted to show you today is I have this very useless source file again, which is called regular intrinsics.c. which is a simple authentication method where we have an if statement which checks whether a given global authentication variable equals 0, and if it doesn't, then it will tell us, nope, go away, and if it does, it will execute our abacus again. You see that this variable is initialized with 0, so as the program stands right now, there is no way we can get to the abacus execution. But turns out that before that is another memcopy operation, where we're trying to copy exactly 96 very useless characters, as you see up here, from one buffer to another. Just imagine that this is a proper application and there's a proper memcopy which copies exactly 96 bytes. What can we do now in the role of a compiler? Was we could go ahead and look for memcopies. We could also go ahead and look for memcopies that copy exactly 96 bytes. We could go ahead and look for memcopies that copy 2,638 bytes, whatever. Like, we could agree with ourselves for a given size that we're interested in and then tap into the processing of this memcopy operation. Now, what I did with my plugin was doing exactly that. I looked for a memcopy operation which copies 96 bytes and extended that copy operation by exactly 1 byte, and that byte will override our authentication variable. And now, if I show you how this works, I can compile again with my malicious plugin. And if you look at the source code again, we couldn't actually execute the Abacus application anyway, except since I compiled it, now all of a sudden the authentication variable equals 0. Or equals 1, sorry. Now if we execute, we see the Abacus again. This is what an attacker could do. If you look at how this looks in the binary, it is rather stealthy. I know there's probably some very, very good reverse engineers in the audience, but honestly, to figure out that this inline memcopy function copies exactly 1 byte too much, as you can see on top of the screen, is a very, very hard task. So if you're looking for the bug that this compiler plugin inserted, I'm wishing you very good luck in trying to figure out how this memcopy was supposed to work originally. All right. Yeah, again, how did I do this? I tapped into 2 different compiler passes. I figured out where the original call was located. I remembered where in the source code it was. Thankfully, the RTL representation still stores source code locations, which means if you look at something in source line 24 in Chimple, you can figure out which RTL instructions the source code line 24 refer to in the RTL representations. Which means that in the end you see 5 instructions which equal your memcopy. And in the second pass that I added, I looked for the inline memcopy and added my 1 byte copy. Now the interesting functionality that you could add doing so is that actually through the memcopy operation, a given attacker could hand over configuration data, which means not only the 96 bytes could be an indicator for the plugin, but also the content that's being memcopied with or without use whatsoever, could contain configuration data that the second pass of the plugin could fish out, which means that as an attacker writing source code that we want to contain a bug once it's compiled, we could insert a very well-crafted string or a very well-crafted piece of data which tells the compiler where to apply a given modification that the compiler pass then will insert. And these are very tricky bugs, as you just saw, that are in the end very hard to find. I see I have 1 minute left from my original time, which is amazing because I'm almost done. Now, what would you do about this? I mentioned before, reverse engineering a plugin is not a task that you would look forward to if that was on your table. It would be possible, reverse engineering anything is possible, but in practice, it's not very feasible. Diffing binaries and finding pieces of source code that were added is possible. Diffing binaries and finding single instructions that were added is tricky as well. You would have to have a very fine-grained diffing process, and you would probably spend a lot of time looking at false positives. What is the thing that you could do about this was relying on reproducible builds. And I mentioned this like I know what I'm talking about. I have not actually looked into how reliable reproducible builds would be in guaranteeing that no malicious modifications were taken. But this is the thing that I could recommend. And something that is absolutely and totally and undeniably recommendable is look at your make files, watch your build scripts, take care of your build chain. Let no one ever touch your compiler. Let no one ever add binaries to your compilation machine. Look at your build robots and review them all properly, and don't let anyone else, like me, touch it. Awesome. 10 seconds left for questions.
Thank you very much. Are there any questions, indeed?
Silence. Yeah, sure. I'll be around all day. And
awesome. Then I want to thank. Oh, yeah. Then I want to ask for a very warm applause to thank her.
Thank you. Thank you very much.